Let's draw together the Slutsky matrix. I know it's somewhat of a painful exercise, but I think it'll help your understanding. So we're looking at a compensated demand change when the price is changing so as to keep utility constant, right? The first column, first row entry is the change in the demand, the Hicksian demand for the first commodity when the price of the first commodity is changing. And here on the first column, we're going to keep changing the price of the first commodity, but measure the impact on the Hicksian demand for other commodities. So the second entry here, we would be looking at the change in the Hicksian demand for commodity 2 in response to the price of the change in the first commodity, right? And all the way at the bottom, we're going to get the change in the Hicksian demand for commodity L in response to the change in the price of the first commodity. So keep changing the price of the same commodity, the first one, and look at the impact on the Hicksian demand for all other commodities, including the same commodity impact. Then for the first row, we're going to do the opposite. So we're going to keep looking at the same commodity, the first commodity, but keep changing the price of different commodities and look at the response on the Hicksian demand for the first commodity. So the last entry here is going to be the change in the demand for the Hicksian for the first commodity in response to a price change for commodity L. Last entry now, because the Hicksian demand is the first order derivative of the expenditure function with respect to price, I can actually rewrite every entry on this matrix. I'll just do it for one, just so you get the idea, and I'll do it in red, and I'll write on top of the matrix just to show you. Here, what am I looking at? First, I have to look at the Hicksian demand for the first commodity, right? And then I have to take the derivative of that with respect to the price of the Lth commodity. But what is the Hicksian demand for the first commodity? Well, that's the partial derivative of the expenditure function with respect to the price of the first commodity, right? So this is the change in the expenditure function when the price of the first commodity is changing. That's the Hicksian demand for the first commodity. And now I'm looking at the derivative of that with respect to price. So I have to take derivative again with respect to a change in the price of the Lth commodity. This is now a second order derivative. So each entry can be rewritten in this way. And this is very interesting because it's going to help us establish that, first of all, because the expenditure function is concave, second order derivative is by definition negative semi-definite. So that's number one. So all of the entries in the diagonal here are going to be negative or equal to 0. The second interesting result, and this is even more interesting, is that because the expenditure function is real valued, if you apply Young's theorem, it doesn't matter what the order in which you take the partial derivatives. So this here expression that I've written is actually equal to, and I will change color, this is equal to the change, the second order derivative of the expenditure function with respect to first a change in the price of commodity L, then a change in the price of the first commodity, right? So the order in which I take these derivatives here is irrelevant. These two expressions are equal. That's Young's theorem. Well, guess what? what I've written here in green is actually this entry right here. So I've established, because the expenditure function is real valued, and a property of real valued function is that the order in which I take partial derivatives is irrelevant, this element on the Slutsky matrix is equal to this one. And similarly, this one is equal to this one, etc., etc. The Slutsky matrix is symmetric. The symmetry of the Slutsky matrix is a new result we didn't have before. When we derived the Slutsky matrix as a result of warp applied in the context of a compensated price change, we showed that warp was equivalent to the negative semi-definiteness of the Slutsky matrix. Here we have negative semi-definiteness, but in addition to that we get the symmetry result. And we get the symmetry result as a result of the real valued nature of the expenditure function and Hoteling's lemma, which we derived, which follows from the paradigm of utility maximization and expenditure minimization. Now, symmetry result is really the continuous statement of in a context where we already assume the existence of a utility function, right? So we already assume transitivity of the consumer's preferences. This is the equivalent to the strong axiom of revealed preference in discrete terms. Imposing the strong axiom of revealed preference will also give you the symmetry result. And the symmetry result is very deeply connected to the transitivity of the rational preference relation. And I should conclude by saying that this is arguably a non-obvious result. Why is it non-obvious? Because it's not particularly clear, I suppose, or obvious that these two items here would be the same, that the impact on the Higgsian demand for coffee resulting from a change in price for tea is the same as the change in the Higgsian demand for tea resulting from a change in the price of coffee. That is not intuitive.